Thanks, Una. Can y'all hear me? As Una said, my name is Elyse, and I'm a design system engineer at Indeed.com in Austin. We're the world's #1 job site, so if you've been job hunting, you've probably heard of Indeed. And today I want to talk about our working theory of components and how to implement this theory with our current tools. So let's start with another theory, the law of gravity. Newton's law of universal gravitation states that gravity, a mysterious, unexplained force, works on all objects in the universe. Objects attract each other based on their mass and distance. More massive objects will attract each other with a greater gravitational force. This is what sends the planets in their great orbits around the sun. Newton's Principia Mathematica was published in 1687. For the 150 years after, the greatest mathematical minds in Europe used Newton's laws of universal gravitation to discover and prove truths about the celestial world. Astronomers worked out increasingly sophisticated descriptions of the orbits of the planets, called tables. The tables showed where the planets would appear in the sky, and Newton's math always matched the real observations that could be made. But small discoveries began to accumulate that didn't make sense. The first observation of what would later be known to us as the planet Uranus didn't fit into the math. Some planets, like Jupiter, seemed to be moving faster in their orbits than in previous observations, and that couldn't be reflected in the math. And many began to wonder if Newton's laws were not universal after all, if there was a flaw in the theory. But not Urbain Le Verrier. Le Verrier was a French astronomer who, while not an excellent observer, was an unparalleled mathematician, dogged in his calculations. In 1846, he posited that Neptune had to exist, based on the math of the orbit of Uranus. And within a month, an astronomer in Berlin found Neptune within 1 degree of where Le Verrier predicted it would be. As a colleague put it, he found the planet au bout de sa plume, at the tip of his pen. In response to claims that the inaccuracies and unknowns meant Newton was wrong, he wrote, "If the tables do not strictly agree with the observations, we will certainly not be tempted to charge the law of universal gravitation with inadequacy." In other words, if the observations of the planets and the mathematical tables don't match, we shouldn't immediately say the law of universal gravitation is inadequate or wrong. In Le Verrier's eyes, there was no need to toss out gravity altogether just because there were some gaps in our knowledge. He was committed to the theory and taking it as far as it could go and learning more and more about the world. Certainly, they didn't know everything. No one knew how gravity worked, even though the math made sense. Le Verrier believed that as time passed, we would improve upon our understanding. Over the past 15 years, our understanding of the world of front-end development has changed. More rapidly than our understanding of the universe, to be sure, but we have been iterating constantly on our working theory of how to design and code for the web. When CSS Zen Garden came out in 2003, we were, quote, stuck in a time when no one was considering CSS seriously, like Cameron talked about this morning. We collectively fell in love with CSS, with sharing styles on many elements at once. And then came jQuery and the separation of concerns of our HTML, CSS, and JS. Do you remember this? A developer should be able to change the markup in an HTML template without worrying about accidentally breaking a CSS rule or some JavaScript functionality. But as we began to build web apps, these complex interactive structures with layers, options, and states, our attention turned to tools that would help us write modular, flexible code. We learned how to do responsive web design and to use Sass to write reusable CSS. In the 2010s, we gained powerful tools like NPM, Webpack, and React. On the design side, we moved from Photoshop to Sketch, and now we have tools like Abstract that are slowly narrowing the divide between design and code. Our needs have changed, and our tools have improved, and we are updating our understanding of the world. The tools we have today didn't exist 5 or 10 years ago. We couldn't be having this conference in 2008. We had no frameworks with which to build a web app with components, no NPM with which to share packages, no way to break up components and isolate them. We've used the tools we have not just to create solutions to the problems we face, but also to create new tools. And these tools aren't just helping us do our job, they're changing the way we can even conceptualize our work. We're building on what we learned previously and filling in the gaps and the unknowns. And we're coming to a new understanding with these new tools of how to do the front end at scale, design systems. A design system promises consistent, cohesive visual design, user experience, and code across projects, pages, and team process. Last year at Clarity, we talked a lot about why you might need a design system and how to get your company to invest in one. This year, like Leverrier, we are committed to this theory. Even as our tools are changing and we're trying new things, we've reached a consensus on this idea. So I want to talk about the next step, understanding how to apply this theory in our everyday work. How do we make sure our systems live up to the promise that Nathan describes here, enabling a consistent experience spread across products and sustained with a dependable, predictable practice? What is our working understanding of a component today? How do we test this theory? In the early 1850s, Urbain Le Verrier was calculating the orbits of every single planet. He intended to create a complete set of tables of the orbits of all of the planets and showing where they would be in the sky at any given time. First, he mapped out the actual orbit of each planet based on observations. Next came calculation. What did Newton's laws predict the orbit should be, given the known gravitational pulls of the planets and the sun? Any discrepancies between the observations and the theoretical math would have to be resolved and explained. The mathematical representations of Venus, Earth, and Mars all behaved properly. The calculated version of each planet produced a chart that matched the one formed by the observational record of the 3 material planets making their way around the sun. One, though, obstinately refused to conform: Mercury. Mercury's orbit shifts forward incrementally each time it orbits. As the planet wheels around the sun, its orbit makes its own gradual orbit, creating a flower petal effect. And this shift is too large to be explained only by the pull of Venus and Earth's gravities. Leverrier, in his book-length report on Mercury, wrote that the likeliest solution was, quote, a planet, or if one prefers, a group of smaller planets circling in the vicinity of Mercury's orbit, providing an additional gravitational pull that would explain everything. He named this possible planet Vulcan. In the years after, astronomers all over the world observed objects near the sun that they believed were Vulcan. On July 29, 1878, a total eclipse would cross America's west from Montana to Texas. Scientists all across America scrambled to make plans to see the eclipse, and getting a clear observation of Vulcan was the biggest prize. James Craig Watson, an American scientist who had made a reputation for himself by finding asteroids, was determined to find Vulcan. Using a small telescope, a setup of cardboard circles, and a sharp pencil, he plotted the transit of an object as it moved in front of the sun. And many other astronomers saw this object during the eclipse too. For many of those observations, the math worked out quite well. Vulcan, if that's what was being observed, fit neatly into the explanation of Mercury's orbit. But in time, observations of Vulcan dwindled, and people began to doubt that it existed. For years, the question of Mercury's orbit created discord and disagreement between astronomers. We know now that Vulcan does not exist. The observations of Vulcan were most likely sunspots or nearby stars. But people kept discovering Vulcan because it fit into their understanding of the world. The limitations of their tools and knowledge at the time kept the answer just out of reach, but they never stopped trying out ideas. They had no way to explain Mercury's orbit without Vulcan, and so they searched to find answers to the unknown. We, too, are trying to find solutions. We have constraints, business requirements, deadlines. We may feel stuck with our legacy tools, like Watson's cardboard circles and sharp pencil. It can be difficult to work with those limitations, and we think we can't keep up with the new science. Often, it can cause conflict between us as we struggle forward to a better understanding. We're seeing this a lot now in our community with the struggle over CSS and JavaScript. There's discord among us over what tools are the best, where and how to write your styles, how to write performant code. We had a gap in our knowledge. How do we create components? How do we solve for maintainability, reuse, and scale? Based on our experience of the world, we turned to varying solutions to try and solve this. For some, CSS tooling and methodologies. For others, JavaScript. We created new tools and made decisions based on these big new ideas we had, combined with our practical technical needs. Yet in all of the disagreements about tools and frameworks, we're working towards the same core idea. We want isolated components that we can reuse, styles that don't conflict, and an easy authoring experience. So what is true about this concept that we've believed for a while that still holds up? What do we know about components and how to build them that solves for the value of a design system, consistency, reusability, and maintainability? We know that if a component is too big or complex, if it has so many options that it's hard to understand, it's not useful to us. We know that if we can't reuse a component in many places, or if it's so small and specific or difficult to customize, it's not useful. We know that if a component is buggy and hard to test, or if it looks or behaves differently than expected in one place than another, it's not useful. So at a high level, we know that a component needs to be three things. 1, easy to reason about. 2, context agnostic. And 3, independent and isolated. First, a component is easy to reason about. Being easy to reason about in some ways is gut feel. It isn't only the size of the component or its complexity. Something that looks simple can be deceptively complex, and some components that are hard to code are not difficult to conceptualize. Too many options or variations means that there will likely be fragile bugs. If it's difficult to ascertain if some code or styles are necessary, things get removed, or worse, left. It's hard to test whether or not all of the combinations work, or understand where all the variants might appear in your app. On the flip side, too few options mean a component is pointless. I've gotten requests to make a box or panel component, literally a box with a border and maybe a background that you can put stuff in. What kind of things? Any things. It's easy to reason about, sure, but it's so vague that in the end it doesn't get used. There's a spot that's just right, where the component is used for one or a few use cases with enough options to make it flexible. As a rule of thumb, if it gives you a headache and you can't hold all the options and variants in your head at the same time, it's probably too complicated. Watch out for mockups that use the component with tweaks every time. If the text is a different style, or there's a different button, or it only has rounded corners when it's in a modal. In the code, watch out for too many properties, states, or variants. Sometimes components come this way based on the design needs, but this can also build up over time as developers add features. If your project is like mine, where many teams use the components, sometimes those teams' needs diverge. If you get a lot of bugs where the component doesn't look or function properly based on context, it's likely that developers are overriding it in ways that it can't handle. This either means it has too many options, or it could mean they're overriding a too generic component, like a panel, to do more things than it really can. In most of those cases, a good solution is to split the component up into smaller, more specialized components that fill each use case more precisely. If there are common combinations, you can create parent components for those. Components being easy to reason about isn't simply about the ease of reading code. The harder battle many times is adoption and use. Getting teams to adopt components and use them relies on their ability to understand what the component is for. Often I see developers say they couldn't use a component because it didn't offer the right options that they needed. Half the time, they're right. The other half of the time, they didn't recognize the options that were available. And a component must make it clear, whether through code, documentation, or examples, what it can do for your developer or designer. So a component that is easy to reason about should be flexible enough to support all of its use cases without being unwieldy or confusing. Second, a component is context agnostic. One of the greatest values of a design system is reuse. We want to take that button or card or comment block and use it all over our projects. The increase of consistency and efficiency is crucial to the theory of a design system. To fulfill this, a component must be context agnostic. Simply put, a component shouldn't need to know where it lives to look or behave properly. One way to be sure your component isn't going to be affected in one place by styles meant for another is to define your key selector or your component namespace only once in your code base. This mainly means that there's one file that contains the component's primary class name. This isolation can be done by namespacing your CSS, like with BEM-style unique classes. Or if your tech stack allows, you can write isolated CSS and JS styles. Either way, the result is the same. We know we can find a single source of truth for that component's styles. It's hard to give up the cascade, but use unique classes rather than letting styles inherit from a parent element. Setting styles directly on the elements that need them ensures the markup structure can change without regressions. This lets our component live comfortably in a variety of contexts and change over time. Having a namespace for the component also makes it easy to reason about, whether you're viewing the DOM in the browser developer tools or the CSS in a code editor. A component being context agnostic also means it needs to function properly and consistently across contexts. A component should not have logic that controls functionality outside of itself. To be context agnostic, a component should have no external state. Data down, actions up. Take, for example, a call to action card component. This card has a button, and when the button is clicked, a modal pops open. It would be easy enough to write code that pops a modal on click. And that will work great until we want to do something different with that card. We want different functionality. So instead, your card button should bubble up an event. Hey, I'm a card button, and I just got clicked. Let it be up to the parent component or the application itself to determine what to do when that event occurs. You can set styles in the component, like active states or indicators, but keep them generic. If a component is supposed to look or behave differently in different contexts, make sure the logic behind those changes is well defined. Likely, the component might need to be split in two, so styles are more isolated. Sometimes the changes aren't necessary. Sometimes the best solution is not a shared component at all, but implementing that feature, as Lynn said, as a special snowflake. A component that is context agnostic should be reusable. It may only be a simple call to action card, but it should be able to live many places in your application and do many things. Third, a component is independent and isolated. To be context agnostic, a component must be independent and isolated. But isolating our styles to a component gives us more than just the flexibility to use a component anywhere. A component being independent and isolated means it will look correct in an isolated environment. It doesn't rely on the presence of styles from a parent container or the global page. It has good defaults, from how it looks standalone to accessibility settings or default text. Consumers of your components need to be sure that they will work and look correct straight out of the box. A component should import all of its own dependencies. We're familiar with this pattern in JavaScript components, where we import packages as needed. And the same pattern in CSS is equally useful. If it uses buttons, it should import buttons. If it doesn't use breakpoints, it doesn't need to import breakpoints. This gives you confidence in what is there and makes it easy to test whether or not an imported file is actually used. Depending on your stack, importing styles this way may require CSS duplication if you kind of get recursive imports of things. You can write this in your own app. You can use kind of a flat structure style sheet. Or if your tech stack allows, you can embrace generated class names, which neatly solves the problem of isolation. Completely isolated components means you now have the ability to test with confidence. You can generate each component into its own page by itself and run visual regression and unit tests on them. We know then that any bugs we catch in that isolated environment are in the component, and any bugs elsewhere, like production, are byproducts of how the application and the component interact. Isolation for testing also means that your component tests only itself and doesn't rely on the presence of a parent container or a child component. Don't test the autocomplete functionality by testing to see if typing in the text input works. Let the text input test that itself. Test the autocomplete by making sure the dropdown appears, that you can select from it, clear it, and so on. A component being independent and isolated means that we can be more confident in its quality, enabling our clients, other developers, and designers to trust in our library as a useful tool for them. It also means we don't need to hobble the creativity of our designers for the sake of code predictability. We can isolate changes, test them, and know we aren't impacting anything else. If you have components that are isolated and independent of their siblings, and that can live in any context, you can now use other components by composition. Composition simply means you can pull in another component into yours and compose something greater. A component can import or reference another component in its markup. In many cases, it might pass an adopted class or wrap the component in a parent class. So if it needs to make some style tweaks, it can do that safely. It can pass props to a component, changing the content and options, such as the text, or whether or not it has an icon, or how many results to show. If you need to use shared styles or mix-ins, you can import those helpers in your Sass or CSS. If you're using CSS and JS, all those styles are written per component and imported in your JavaScript. And in your component's JavaScript, have your component bubble up its actions, so you can grab those and do whatever needs to be done in your app to meet the requirements. Our theory of components should be applicable regardless of our tools. What works for one project may not work for another. But when you find things that don't work, gaps in our knowledge, that doesn't mean the whole theory is broken. You may be using Sass or CSS modules, React or Ember, or maybe not anything that new and hip at all. The majority of us don't get to use the newest and hippest technologies. You might not feel you can innovate if you work for a slow-moving company on an old tech stack. But there are many reasons we can't and shouldn't throw out our projects and do a huge rewrite. At my last job, we wrote a shared component library with templates and handlebars for a PHP app with Sass. And now at Indeed, we're using Sass with React components, but also providing templates in Soy for Java projects. You don't need the newest, hippest tools to apply this theory of design systems to your work. So instead of getting frustrated, consider how you apply the theory using the tools that are available to you. Test the theory. We believed we observed Vulcan because it made sense, but no real Vulcan ever turned up. Scientists posited that perhaps it was asteroids or comets or a variety of things as they poked and prodded at the theory, trying to find a solution. It took almost 60 years to add the information to the theory that would explain Vulcan. In 1913, Einstein is working on his theory of general relativity. He does a calculation to see what the math predicts for the orbit of Mercury. Can his theory accurately describe Mercury's inexplicable orbit? The core concept of general relativity is that space and time can be changed by the presence of matter. So a vast mass like the sun creates curves in space-time. So Mercury's orbit shifts because that's the path it has to take through the curved spacetime created by the huge mass of the sun. Without curved spacetime, you need some other object's gravity to pull on Mercury, like Vulcan. With curved spacetime, Mercury behaves exactly how it should. But Einstein didn't disprove Newton's law of universal gravitation. Gravity still exists. The planets are still held suspended in their orbits thanks to gravity. The tables of planetary orbits that Leverrier calculated in the 1850s are still accurate, although better measurements have made them more so. General relativity updated our understanding of the world. It filled in gaps and created a better framework. Finding a new answer doesn't disprove the theory. It builds upon it, strengthens it. Many astronomers worked as observers. They experimented, saw, and recorded how the world really was. Others, like Leverrier and Einstein, worked as mathematicians, conceptualizing a theory that pushed our knowledge farther. So consider as you work both aspects. Your project has a tech stack, you have limitations and constraints. Your components are your observation of the world. But to know what to do with those observations, you also have to have the math and the concept. We've described what a component must be at a conceptual level to fit into the theory. When you're building your design system, how do you know if your components fulfill your particular application of the theory, the observation that depends on your project's requirements and technical constraints? At Indeed, my team put together a document that lives in our project's repo in the contributing docs that is a component checklist. It outlines the 3 high-level concepts I spoke about earlier, being easy to reason about, being context agnostic, and being independent and isolated. But it also contains a much more concrete list of what a component must do. And here's some examples. To be easy to reason about, a component must be self-documented with comments for all the properties, options, and variants. It must have both design and technical documentation that explains why it exists, what it's for, and how to use it. It must have unit and visual tests so we can be sure we know how it looks and behaves. And it must have appropriate default states and error states that make sense. To be context agnostic, a component should have no layout, no margin, float, or other properties that affect the whole component. It can have styles inside itself to lay out children, but nothing that would keep it from being used in a variety of contexts. It should look appropriate in all supported browsers and on all supported screen and device sizes, including touch devices, mouse-operated devices, and assistive devices like screen readers. It should have accessible visual styles and ARIA information, and it should look and function correctly in both left-to-right and right-to-left languages, which, at least at Indeed, is important to us for internationalization. To ensure a component is independent and isolated, it should only affect itself. It should not bind any functionality to style classes or affect functionality outside of itself. It should define styles and elements using a unique class rather than relying on inheritance. It should define or import all its own styles and only define the component namespace in one place. And it should work as a standalone component, but also when it's used by another component or application. This checklist, defining what a component should be, gives you a tactical way to test your observations and thus test this theory. Having this available makes it easier for anyone who works on components to do the right thing. We have a team that builds many of our components, but many teams use them and they make changes or bug fixes. And this checklist keeps everyone on the same page. With it as a reference, we can be sure we've done everything necessary to make a component that will work as we expect it to and be a valuable part of our library. And we keep the theory and promise of design systems close at hand in our everyday work. Consistent, cohesive visual design, user experience, and code across projects, pages, and team process. Every day, we test this theory. After formulating the theory of general relativity, Albert Einstein pondered what would happen when a huge object in space was disturbed, like an exploding star or 2 black holes that sucked each other up and collided. And he predicted that any cosmic event that disturbs space-time with sufficient force should produce ripples in gravity. Scientists didn't agree. Even Einstein didn't agree if this would be true. These ripples, even if they were real, would be so small by the time they got to us, we wouldn't be able to detect them anyway. Many believed that the ripples were just artifacts of the new math, that somewhere the calculations were wrong. At the time, many scientists didn't even believe black holes were real. Einstein's theory explained many things, but it also opened up new questions. The pursuit of science is more than the pursuit of understanding. It is driven by the creative urge, the urge to construct a vision, a map, a picture of the world that gives the world a little more beauty and coherence than it had before. Over the last half-century, there has been an experimental quest to detect these gravitational ripples that Einstein predicted. An international team of scientists has been building a pair of colossal gravity wave detectors called LIGO, the Laser Interferometer Gravitational Wave Observatory. This took almost 50 years and cost millions of dollars, and the LIGO teams were not even sure if they would detect anything. LIGO had its funding granted, revoked, restored. People questioned, doubted, mocked them. Yet the LIGO teams persisted because it is crucial to think beyond today's understanding of the world, to give the world a little more beauty and coherence than it had before. Out in space, two black holes circle each other, churning up space and time until they crash and merge into one enormous black hole, an event outputting more than 1 trillion times the power of 1 billion suns. Black holes collide in complete darkness. None of the energy exploding from the collision comes out as light. That energy emanates as waves in the shape of spacetime, as ripples in gravity. An astronaut floating nearby would see nothing, but the space around her would ring. She would hear the wave. Almost exactly 100 years after Einstein presented general relativity in December 2015, LIGO detected that collision. We heard two black holes collide. LIGO not only changed our working understanding of the world, they accomplished one of the greatest feats of modern science, and yet again, open up new questions for us to ponder. Our work may not seem so grand. What could be grander than black holes, planets, celestial motion? But even firmly planted in our mundane, earthly work, we too can think like scientists, continually working to expand the theory, confirm it, and strengthen it. We are experimenting with this theory of design systems every day as we work. What we learn will add to the theory and help us move forward and create even better tools to improve our work. Searching for new solutions might even propel us forward so far we have as many new questions as we have answers. As we work together today and tomorrow, and in the months and years to come, keep thinking beyond today's understanding of the world and onto tomorrow's. Thank you.
Awesome. Awesome talk.
You're not on yet.
Hey, awesome talk.
Thanks.
Thank you. Please take a seat. Popping out all over the place. You never know where I'm going to come from. Sorry, I'm having too much fun with this mic. Thank you.
Sorry.
Welcome, Elyse. Thank you for that.
You are welcome.
First of all, beautifully designed slides.
If you saw the credits, it wasn't me.
And second of all, awesome science metaphors. I love those. So what inspired that?
A couple books actually, and some work that I did at my current job. So as I mentioned in the talk, my team, we wrote this document, and this is one of the first things that I did when I joined our team. I collaborated with a couple of my teammates to create this checklist and kind of define what our concept of a component was in our library. And then there were a handful of books that I had read. Did anybody else go to the eclipse this year? Anybody travel to see totality? I see a couple of hands. So just before that, I read a book by David Barron called American Eclipse. These are all on my slides resources page, so if you want the links, you can get them. And it was about the 1878 eclipse, about looking for Vulcan in the eclipse. And that kind of led me to this other book called The Hunt for Vulcan, which goes into more detail about Leverrier and how the whole like finding it and the math and everything. And then the last book I read was Janna Levin's Black Hole Blues, which tells the story of LIGO. And she published this book before the first detection that LIGO ever made. So she's telling this story about building this thing and kind of just like trusting that there might be something out there and just knowing like this like struggle of like progress and how hard it was to look past what we know about the world and say, we're gonna kind of keep thinking forward. And so I was reading that and trying to kind of like pull all of these different things into this idea of what is the theory that we're working with right now? Because it's so different than what we were doing 5 or 10 years ago.
Do you have any more to say about how to build regardless of the technology you're working with and the steps that you need to think about in order to be effective? Yeah,
so one of the things that I feel really strongly about this because there's so many new tools and things changing and you hear like, oh, we're using this new thing and that new thing and this framework and that framework and, a lot of us, I work at big product companies and I always have, and when I was at Retail Me Not, we had an old, 5, 8, 10-year-old PHP app, and we weren't gonna like throw that out and start over, but we still wanted these new conceptual ideas, that the industry was coming out with, I think it would have been a mistake to throw out everything that we had and do a rewrite. So we kind of built our own custom setup where you could have components, like a single component in a folder with its HTML, CSS, and JavaScript all together. And we built custom CSS deduplication, and we built all these tools, and it took a long time, and it was kind of difficult and painful to do that and to build all this custom stuff, but it was less time and less difficult than tossing the entire application, that was in use and making us millions of dollars and like rewriting that. And I think there's a lot of like frustration of like, oh, I want to use this hip new tool, like I want to use this new framework, I want to try this, but you can still take this concept that we're kind of settling on as an industry and make it yours in your own tools, and it's really sad for me to hear people go, well, we can't do that, it's impossible for us to do that. As for your second question about how to be effective in doing that, I'm not even going to try to give advice because it depends so much on your team and your particular situation, whether you have a team or whether you have resources and what your stack is and what your company does and how much they're willing to invest. But don't feel so limited by your tools. There are ways to use this theory of design systems and theory of components regardless of what your tech stack is.
Yeah, that's good advice. So last question. You mentioned during the talk that components should be context agnostic and isolated. Mm-hmm. How would you deal with a situation when you have a component that should look slightly different in different contexts?
Yeah, so there's kind of a variety of like solutions and honestly like none of them are quite perfect. And this is another place where I wanted to talk kind of about this theory, but I am not going to try to tell you exactly how to solve that problem, right? You can do something that's kind of referred to as like adopted class. So if you use a component and when you call the component, you say like, and I also give it this other class. So like, here's the text input, and then when I reference that component, I say also the autocomplete text input or whatever. And so then if I'm applying styles, I mentioned components shouldn't have margin or like layout properties, right? Like you don't want a text input to be like floated left or only so wide, because then if you put it in the autocomplete, now you're messed up and it doesn't work. So you can pass this kind of adopted class. You can also reference parent classes. There's also a school of thought, and I know Ben Frayne, he wrote Enduring CSS, which I've learned a ton from, and he pretty strongly says, just make a new component. Like, this whole reusability thing is bunk. If you need a text input in the autocomplete, just write one. Text inputs over here are a totally different thing. And depending on your setup, depending on the way that you reuse things, that might be a better option. But those are kind of the three, I think, most common ways to do it.
Awesome. Thank you, Elyse.
Thank you.